All right, so we're just going to finish off this question. And the nice thing about this question is that it kind of ties together everything we had kind of been working on up until this point in the energy unit. So what we want to know is what constant braking force would have to be applied to the roller coaster at point E to bring it to rest in a horizontal distance of 5 meters. Now, one thing I noticed in doing this is this should be a 1,000 kilogram roller coaster. I missed the 0. We know that makes sense because 100 kilograms could be about the weight of one person, and so we need to figure out there's a bunch of passengers in this thing, so it better be more than 100 kilograms, the overall roller coaster, right? So when we come down here, we know that the mass is going to be 1,000 kilograms. And we also know, and for the purposes of the argument, we'll use, there's probably some rounding error in here when I did this calculation as my grade 12 self. So we'll use the answer of 8.8. So we know that the velocity at point E, right, we'll call it V1, right, because the coaster has come up to here. We'll call this V1 at point E. And then the track goes horizontal. We'll call this V2 over here, right? And V2 is going to be equal to 0, right? Because it's coming to rest. So V1 we know is going to be 8.8 meters per second. And we know V2 is going to be equal to 0 meters per second. And we know that the horizontal distance that this roller coaster needs to stop in is 5 meters. Okay, and so we know that work is defined as the change in kinetic energy. And so we can write, we'll do two things here. One, we'll write out the two kinetic energy statements. So we know that there has to be a half mv2 squared minus 1/2 mv1 squared. Okay, so that takes care of the right side of the equation. But we also know something based on the first day of work, of lessons, what work can be defined as. And in work, we can define as the force times the distance. Okay, now I think we've checked off mostly everything. So the force that we need to, well, let's take a look here for a second, the velocities. Okay, we know V1, what it arrived at point E with, right? That's the 8.8 we just solved for in the last question. But we also know that the final velocity, the cart is coming to a stop, so we know that it's 0. So here's what we've got. The force times the distance has to equal negative 1/2 mv squared. Okay, v1 squared. I'll add the 1. Okay. And so why don't we just at this point plug in some numbers and see what happens. Okay, so the force times 5, right, for the 5 meters, has to equal negative 1/2 times the 1,000 times the 8.8 squared. Okay, and if we type this into our calculator, we should see, I'm just going to do that now, that 0.5 times 1,000 times 8.8 should equal negative 38,720. Okay, and if I divide both sides by 5, we should see, oh, not meters per second, newtons. Newtons, force is in newtons. Okay, so this is the braking force to stop the coaster. Okay, our problems stem from the mass originally this morning. Okay, so that's that. Okay, that's combining like our work energy theorem, work kinetic energy theorem with potential energy, kinetic energy. We're just trying to tie all that together, right? And forces, right? Through work. Okay, so that's that. that's how we wrap up that question. If we come down here, we'll see our familiar Atwood machine. Okay. Now we could, if you guys would like to, under normal circumstances, based on what I've shown you so far, we could solve this using a for statement, and we can also solve this with energy, right? Because right here, block A has some potential energy because it's been lifted off the ground, right? We know its mass is 15 kilograms, right? We know block B has a mass of 12 kilograms. So obviously this thing's being held here, right? And we want to release this and release like all this potential energy that's stored up in block A and transfer it into kinetic energy for the entire system. Okay, that's what's going to end up happening here, right? We also know that the height of block A, which ultimately dictates how much potential energy is in the system, we have 0.85 meters is the height of block A off the ground. Okay, and so what we want to do is set up an argument that allows us to analyze energy before and what the energy was afterwards, right? And so beforehand, right, I always like writing statements like this, and after will be over here. Okay, we'll deal with the before. So right now, before, right, nothing's moving. So everything, the entire system, has potential energy through block A. Okay, so it's the potential to move, right? As soon as I release my hand, things are going to change. Okay, so in block A, all the potential, or initially, all the energy beforehand is all potential from block A. So we can say M of A, G, right? G is just G, and H of A, right? This is all potential energy, right? The entire system. Nothing's moving, so we're done with before, right? Everything's potential. Afterwards, everything's going to move, right? This entire system. And so we're going to incorporate that movement into the after statement that we're going to see, right? So basically what's going to happen is we're going to release this. Block A is going to slam into the floor, right? And block A is now going to be lifted up off the ground to the same height that block A was initially. Okay, we want to figure out what the speed will be for block A when it hits the ground. Okay, what the velocity or speed is, right, of block A. So let's just write our statement. They're both going to move, obviously. Okay, so we're going to have 1/2 of ma VA squared, right? That's going to take care of the kinetic energy of block A after I release it. And then we're going to have to add the kinetic energy from B. So 1/2 m of B, B squared. And then I'm going to have to add mgh, right? The new height that this block B is going to have, right? So mbghb. Okay, and that's our statement. That's all the components of our statement before and after, right? And they're going to be equal to each other because we can't create or destroy energy. Okay, so we're assuming this is a closed system, so everything's going to be conserved through potential and kinetic energy. Okay. Now, what you should see, okay, is obviously like these we saw with our when we worked with these questions in the past, and we saw the accelerate. This is going to accelerate this way. Right? We saw just one acceleration value, right? Whatever it was. Right? And that's because this system is tied to one another. Right? Well, if I see one acceleration number, I better see one velocity number. So the velocity of B should be equal to the velocity of A, the speed of A will be equal to the speed of b. The velocities will be opposite in direction, okay? But you'll notice I'm not drawing vectors on these. Okay, so we're not really taking into consideration the direction here. It's just the magnitude of the velocity. So speed, the speed of A and the speed of B. So these are just going to drop out to be just speeds, right? It's the same speed, right? And what your answer is going to be is we're going to find the speed of block A, right? But you could say the velocity of block A would be whatever the number is down, and the velocity of block B would be whatever the number is up, right? We know everything else in this question, okay? It's just the velocity value that we're after. Okay, so now it's just like a little bit of I'll call it trickery with math, but it's not really, right? You guys know how to deal with a situation like this. So let's just have a run through this with the algebra and see what happens, right? I'm going to move this to the other side. Okay, that's what I'm going to do. Okay, so we're going to go MA, the mass of A, times the gravitational constant multiplied against the height of A initially, right? And that's going to be, we're going to subtract off this term over here, right? And we're subtracting because I took it and moved it to the other side. So I'm going to see the mass of B times G times the H of B, right? And that's now going to equal 1/2 MA B plus 1/2 MB B squared. Don't forget your squareds. Okay. Now there's a little bit of math here that I could do. Well, I see between these two terms, right? I see a 1/2 that's in common, and I also see a V squared that's in common. So let's factor that out. Okay. We'll say, okay, let's do that. Then you go MAGHA minus MBGHB has to equal 1/2 B squared MA plus MB. And if I were to isolate, we could just start trying to get velocity by itself, right? So we could go, okay, well, let's multiply both sides by 2. We can do that pretty easily, right? If I do that, the 1/2 cancels out, so that's gone. And then I could say, okay, well, let's divide both sides by MA plus MB. Right? And that's going to equal V squared, right? These are going to cancel. And so we can find the velocity of the entire system. Sorry, I keep using velocity. The speed of the entire system, velocity for V, that's what keeps tripping me up. The speed of the system we can find as being V equals the square root of 2 MAGHA minus MBGHB all divided by MA plus MB. Now the nice thing about doing the algebra like this is this is basically a solution to every question that you see like this, right? If I was asking for the velocity, let's say, right? That's what's nice about solving things in algebra. Nothing gets convoluted by all these numbers that are mixed up in here, right? You have basically a kinematic equation. It's not a kinematic equation, but it's an equation that you could say, under this circumstance, I can apply it to this question, and you could put it on your formula sheet. That's the point I'm trying to make, okay? By doing the algebra, you don't lose, through convolution, all these numbers. Like if you plugged in the numbers, you just have numbers that were just specific to this question, but now you have something that is specific to Atwood machines, right? And solving Atwood machine systems using an energy argument, okay? And you can find the speed of the system through this, okay? If I ever asked you to do that. That's what's nice about the algebra, okay? So all you would have to do now is just plug in all your information, like we know all this stuff, B is going to be equal to 2 times, what's the mass A? Well, 15. And then G is 9.8. And HA was 0.85. Right? And then you go, we're going to subtract off the mass of B, which was 12, times 9.8 times, it's also going to be 0.85. And all of this is going to be divided by 15 plus 12, which is square rooted. Right? So when you type that into your calculator, you should see that the answer, V, or the speed of the system, should come out to be 1.36 meters per second. Okay, which will round to the answer that it was. Oh, I didn't put the answer there. Should be 1.4. Okay, that's how we arrive there. This is an important skill, and whether or not you choose to do this in grade 11 is completely up to you. Okay, I understand that there's a level of it makes things look more complicated than it really is. You know all that stuff sitting in there, right? And so it honestly doesn't matter to me. What I'm trying to do is give you guys a skill that you will eventually need as you go into university. Okay. I think it's better to experiment with it now and play around with it than later when you're paying for courses and things get more difficult. Okay. And just working algebraically is a powerful skill. One that I did not refine until well into university, right? This is something that I started doing in first year, and I wish somebody had pushed me towards doing it in the first place. Okay, makes answers more accurate. You know, it's less time typing out numbers and rounding, and it's less of a pain. And the other thing is, like, if you were ever given a question, let's just think hypothetically here, right? Let's say you have a midterm test question, right? And you do some questions, and you do all your homework at university or whatever, right? And there's a multiple choice question that says, here's the velocity, here are a bunch of velocities, here's your system, and tell me what the velocity is, and A, B, C, D, E, whatever, right? If you guys knew through your homework that the velocity of an Atwood system, sorry, the speed of an Atwood system, the speed at which the blocks move, was equal to this, you've already done all of this derivation work to arrive here. At which point you guys know, if you had this memorized, and if you didn't, not a big deal, you could rederive it, right? But you could say, okay, well, this is just a multiple choice question. I don't need to show all this work. If I had this memorized and I've done it in the past and I know it works, then your multiple choice question could be over in a matter of 2 minutes. If you write this down and you plug in the information that you know, it spits out the answer. And you go on to the next question. Okay. So there are some tricks and benefits to being able to work with algebra, and this is no different than a kinematic equation sitting on your formula sheet, right? It's just applied in a different scenario, answering a different kind of question. Okay, and that's the importance of the algebra. So whether or not you guys choose to do it, I'm not going to push you guys. I'm just trying to open your eyes towards a different way of doing things that's ultimately going to benefit you in the long run. Okay, so that's it. Hopefully that clarifies this morning, at least for part C. I forgot a 0 in the question when I was typing it, and that would be an alternative way to solve an Atwood machine. Okay, so that's it.